Welcome to video number 3 of building your automated AI assistant. In this segment, we will explore how to enhance our AI setup by working with documents and providing more context to our AI system. Documents in this context kind of refer to unstructured data. That's the opposite of what we did in the last video. In the last video, we had configured our base row tools and the data was coming from a database, and that's basically as structured as it can be when it comes to data. And documents are all sorts of unstructured data coming from different sources. So we talk about PDF, we talk about text documents, we talk about I don't know, chat histories from Slack, or maybe data you have in a wiki or on a web page. There are a lot of data sources that need to be organized, and we need to make them usable for our. At first, I would like to give some information about the why and how. So while training large language models provides them with large amounts of knowledge, this knowledge is kind of general. So it does not include the specialized knowledge you will have in your wiki or in your documents or whatever you need for your work in your company. Therefore, the large language model cannot really help you with this unless you give it the knowledge and the context. So, for example, I asked the AI to create the Alice in Wonderland like story, and then I initialized a new conversation in a new chat window. And when I asked the LLM about the story, you can see that the LLM doesn't know about the story. So what we need to do here in order to help the LLM answer my question is to give it the right context. So when I now give the same question with a little bit of context to the LLM, you can see I get a much better and more detailed answer that actually reflects the story here. And that is basically the way we give more information to the large language model if we don't want to or cannot train our data into it. And of course, the manual inclusion of data and context to give to the LLM is very time consuming and inefficient. One solution one might think of is we have really large context windows at the moment. And I think on the Gemini Pro model from Google, you can send up to 2 million tokens in context to the large language model. And of course, this is a way to give context to the large language model, but this will greatly improve the number of tokens that are used, because the context window does not only contain the information you give to the model, the context window also holds the information for the answers and the whole conversation with the model in that particular chat session. Giving it, I don't know, 1 million tokens of context and then having a long conversation back and forth. This will use a lot of tokens, and this will, of course, also drive up the costs because we are paying per token if we use a provider like Google or OpenAI. And this will also slow down the conversation because the model has to go through all of the context for each answer. And the other thing is, if the model gets way too much context and a lot of irrelevant context, it will get confused as much as a human would get confused here. So the right approach would be to manage and organize our documents in an efficient way and to provide only the context the model really needs to give the answer to the question. And when we head back to the overview from our first video, we had this part here we haven't talked about in the second video. That's where vector store and the vector database comes into play, because this can be used to store and retrieve relevant context for our LLM. The way a vector database works is it will store a numerical representation of the data you have stored in the database together with the data. So what that means, for example, when I am here in the quadrant web interface, you can see here I have my document here, which is an image. And over here, I can just copy the vector to clipboard. And as you can see, this is represented by a very, very long number. And the way you have to imagine this is like a multi-dimensional coordinate system. So, for example, when we have a coordinate system here, we have usually 3 axes. We have a x and the y axis, and we have z axis. And this will give us the 3 dimensions we are used to when it comes to our vision. But when it comes to the vector database, we have a lot of more dimensions. So the vector database will usually have between 500 and 5,000 different dimensions, really. So when we have a look at the quadrant interface and have a look at the collections, you can see the amount of dimensions you have here. In my Midjourney example here, I have 512 dimensions. And each item or each document that is stored in the vector database will be represented by 512 dimensions here. The way we create these vector numbers is by using a dedicated large language model, which is able to create vector embeddings out of the data we provide to it. When it comes to the retrieval part of the information, as everything is represented by a number, and the way this helps us when we want to retrieve data and to find out what information in our database fits best to the question we have for our LLM. So when we have a closer look into this data set here, we have a graph view inside of Quadrant. And if I change my graph view to a more detailed view here, I have the point I have chosen the middle, and you can see there are a lot of data points around. And the way this basically works is that the database will do a similarity search. And that is something you can see in this graph view. The way this sample data set is structured, this is meant to do a similarity search on the styles of the different images. So when I am here in the middle at my original image, the images that are closest to this image are the ones that are most similar. And when you have a look at the outside nodes here, you can see that the styles are much more different. And that's basically how the vector database works. So it will calculate the distance between the vector representation of my search query and find the nearest vector points that are connected to the documents. And then we can fetch these documents and feed them as context into our large language model. And as everything is encoded and represented as a number in this multidimensional vector space, it doesn't really matter that our data has different structures and came from completely different sources, because we will just do a similarity search that fits our query and we will get the right results most of the time here. So that was a little bit of theory. And now I will show you how we can do that in our AI starter kit here. First of all, I will just create a new workflow here. And the purpose of the new workflow is to load documents from a folder in our system into our Quadrant vector store. But first, I will just add a trigger here. And here you can see I can just make a trigger that will watch a local folder for changes. So I can just copy the absolute path to my folder in here, and then I can save it, and n8n will watch this folder for any file that I add to this folder. If you have followed the self-hosted starter kit by n8n installation, you will have a Docker setup. So that means that you cannot just take any local folder from your computer and reference it in your n8n workflow. In our Docker setup, in the Docker Compose file that was in our repository, there is a volume mapping here. And this maps the folder shared in our local system to the folder data/shared. So what that means is when we have the Docker container of n8n, we need to refer to the folder to watch, in this case, to /data/shared. And any file you put in your self-hosted AI starter kit directory into the shared directory will be made available inside the container under data/shared. And that's basically the way how you can share your documents with your n8n workflow. When I double-click my local file trigger node and hit test step, it will start listening for file changes in my folder. And when I just put a file into the folder, you can see that n8n immediately knows about the changes to this folder. And just for the purpose of building this workflow, I will pin the data so we don't have to use the test step all the time. And now we need to read in the file. So we take the read-write files from this node here and we go for read file from this. And as you can see here, the previous node provides the absolute path to our document here. So we can just drag the path in here and test this step. And now you can see n8n has read in the file. The next step in this example would be to extract the text data from the file object here. So we just take the extract from file node here and we choose the appropriate format here. So in this case, we have just a simple text file. So we extract from text file here. And here it wants the data property. And this is by default an n8n data property. So if you happen to rename the data property in one of the previous steps, you have to be aware that you need to change it also in here. And here you will just have the destination property. And when we test the step here, you can see that from the file object, it has extracted the complete text data here. And now we can already connect our vector store here, which is quadrant in this case, and we just select add document to vector store here. And as this video is meant to be just a basic overview about storing documents in your vector database, I will not go into all details here. We will go into greater detail in the following videos. So what we need to do here is we need to select a quadrant collection. Usually you won't have a collection here if you just installed your AI starter kit. So what we do here is we will just switch to by ID and then I will just name it n8n demodb. And when sending the first document over, this collection will be created for you. And as you can see here, the quadrant node has some more points to add here. So first of all, we will need an embedding model. And in my case, I have already installed one and I take the nomic embed text latest here. And the next thing we need to store our data in the vector database is a data loader. So we select the default data loader here. And here I will just keep it at load all input data, but you could also load specific data. So when you have large amounts of JSON data, for example, you can exactly define what data you want to pick from a JSON object. And after we have selected the default data loader, we need a text splitter. And I will explain all of this later on. I just want to finish the first steps here to get this working. And in this case, I take the recursive character text splitter and I leave the chunk size at 1000 with no overlap for now. And that is basically the workflow we need to read in our files to create the vector representations and to store everything in our database. So there are probably a couple of unknowns for some of you here if you do this the first time. So first of all, we have the embedding model here. And the embedding model is a large language model similar to ChatGPT or whatever. And this model has only one job. It should read in data and create vector representations out of the data we can use in our vector store. Technically, you could, for example, just take Llama 3.2 to do vector embeddings, and the model will create vector embeddings, but these will not be as accurate because this model is not trained to do vector representations. It is trained to give answers to your questions. And the other thing is the Llama 3.2 model will be much, much slower than the embedding model. So the best approach here is really to get a dedicated embedding model here, and I will just show you how you do that in a second here. So when we head over to olama.com and go to the search box, you can select embedding up here. And as you can see in the model I have just showed you is at the very top here. And that's the mostly used model when it comes to Olama embeddings here. So we can just go for the model here. And over here we have the copy button for the command to pull down this model onto our computer here. So when I enter Olama pull nomic embed text here, it will download the model. And in my case, this is already downloaded. And if you have followed the installation steps and decided to have Olama in a Docker container, you will need a slightly different command. So you will just need a docker exec Olama and then Olama pull nomic embed text here. And then it will download the model for you and you can use it in your n8n workflow. The next part in our workflow is the default data loader. There's not very much to set up here right now. So you can choose between JSON data and binary data. And as I said before, select if you want all input data or just specific data here. The more interesting part here is the recursive character text splitter. And the reason why we need a text splitter here is we could basically just give any kind of data into this workflow here. And of course, you could have, I don't know, 60-page PDF, or you could have a whole book content here. And when it comes to retrieve information and to search for similarities to our queries, it's better to divide our documents into chunks in order to retrieve the most relevant information for our query here. And the way this works here is we can define a chunk size. That's the number of characters we want for our segments to have. And we can also define an overlap. So for example, when two chunks are split apart, you can define an overlap to keep contexts between the two chunks here. To make this a little bit more visual, I will just show you how this works. So we can just run our quadrant vector node here. And when I double click on my text splitter here, you can see I have the long text over here on the left. And over here, I have the different chunks that were made. And you can see this story is not very long and it was divided into 8 chunks here. And of course, what I could also do is I could just go down to 100 characters and try this again. And now you can see I get a lot of more chunks here. And each of the chunks is stored as a document in our vector database. For example, when you have a very small chunk size like the 128 characters here, you have a lot of granularity. And it really depends on how your document is structured really. So if you have a document that consists of a lot of short sentences, it might be good enough to have a chunk size for 128. But if you have longer text blocks like paragraphs and so on and so forth, it might be better to increase the chunk size. And that is really something that's very much dependent on the documents you're using. One more note on the text splitters here. When I delete this one here, you can see there are different ones here. And the most recommended one is the recursive character text splitter, because this one will look for new lines and double new lines. And that's basically how a lot of text data is really structured in books and on the internet. So for example, when you have a paragraph, that's usually divided by 2 new lines. And if you have a section, that's usually divided by 1 new line. And the recursive character text splitter will try to take this into account when splitting your data here. And if you take the other ones, for example, the character text splitter, it split even in the middle of words. So if you define a chunk size for 100, it will just chunk it up into segments of 100, no matter if it's a complete word or not. And for the token splitter, that's basically the same, just with tokens here. What you can also do is you can try to estimate the paragraph length. So for example, I have a code node here. There's just a little bit of code in here. And this was actually written by one of the models I have in my Olama instance here. So there's nothing really fancy about it. And what this does is when I have the text here at the left and I do the next step, this will calculate averages here. So for example, the token length for an average sentence is 13.5 and the max token length for a sentence is 60. And the same I have here for characters. And the same goes for paragraphs here. So as you can see here, my longest paragraph in this example is 501 characters. And I could just go here to our splitter and just take the longest paragraph if I want to split my document by paragraphs here. And then I can just rerun this. And you can see I have these different chunks here. And I think this one could be the longest. And when I copy my text into a token visualizer, you can see I have 501 characters that will result in 88 tokens for our LLM. And here you have a preview how the tokens will probably be. And when I head back to my n8n workflow here, you can see that the estimated token length here for a paragraph is very similar to what this tool here has calculated. And when I have a look at the UI of my quadrant database here, I can just go to collections. And here I have our n8n demo database here. And you can see here we have the different chunks that were created, stored in our database. And here we have also the vectors stored alongside. And as you can see, this model has created 786 dimensions here. And that's basically how our data is stored here. And now we can just build a simple chat workflow for retrieval of our information. So the simplest version of this would be a question and answer chain. So here we have our chat and we need to select a model here we want to talk to. And I will just take the Llama 3.2 in this case. And then we need to define a retriever. And in this case, we take a vector store retriever because we have just put our data into a vector store. And here I can define how many matching documents will be sent back to us in order to give them as context in our LLM. And I will just go for 5 in this example now. And now I need to connect my vector store, choose quadrant here. And here I need to give it the collection where it should retrieve the information from. And in order to search in our vector store, we need to embed the questions we have for our large language model with the same embedding model we have used before. So in this case, I just take an Olama embedding model and take the same one I used to load our documents here. And now I can just ask a question about the document here. So I can just ask where the character Elara is from. And as you can see, the large language model has found the information in our vector database. So it says here, Elara appears to be from near a dense forest full of whispering trees and so on and so forth. And over here, you can see what has happened. So we have our vector store retrieval. And here we have the query that was sent to the vector store. And the vector store has found different similar documents of our story and will send them all back as context to our LLM. And the large language model will reason about the pieces of context here And you can also see here the internal prompt, which is use the following pieces of context to answer the question at the end. If you don't know the answer, just say you don't know. Don't try to make up an answer. And then we have all of the context that was fetched from our vector database here. And here we have the answer of the large language model. And of course, we can just load all kinds of information here. So I can just save this workflow and set this to active. And first of all, unpin our data here. And for example, I have prepared 2 documents from the n8n documentation here. I have prepared the documentation for the base row node in n8n and also for the base row authentication in n8n. And right now, when I ask my large language model here, what can I do with the base row node in n8n and execute this, it will tell us that it doesn't know about the base row node. So when I go to my file explorer and I take the markdown file for the base row documentation for n8n and copy into my folder here and head back to my workflow to the executions here and hit the last one, I can see here that our base row.markdown file has been read and it has been chunked and stored into our vector database here. And one thing to note here when it comes to text formats is the recursive character splitter is able to deal with different text formats. So for example, when you have plain text, like in our first example, you have double new lines. But when you have a markdown document, you will have a different structure or HTML and so on and so forth. All of the different document types have different separators and different decorations for headlines, for paragraphs, and so on and so forth. And therefore, you can just select the kind of text document you have here. And you can also see this also provides some programming languages, and this will help keeping code together that belongs together and also keep paragraphs together in Markdown, for example. So in this case, we can just set it to Markdown. And now I can save my workflow here. Delete the file here for now and copy it back in again. And when I have a look at my executions here, the file should have run through. And when I look here, I have the markdown chunking here. And then it will have loaded my file into the vector store using the markdown chunking. This also depends on your document because this doesn't have a very strong structure here with different type of headings and subheadings and so on and so forth. But when you have a more complex markdown document, you will also see that reflected in the chunks. And when I ask again, what can I do with the base row node? You can see I get an answer from the LLM and it will tell me that I can create rows, delete rows, and so on and so forth. And now I can just ask the LLM how to authenticate the base row node. And here it will just say you need to refer to the base row credentials page for guidance on setting up authentication. But if I head back to my file explorer here and add some more context for the authentication here and ask the same question again, now you can see I get an answer. The base row node can be authenticated with basic auth, which requires a host username and password to log in with. So that was a basic overview on how to work with documents and vector store on the n8n AI starter kit. And this is, of course, just a part of our AI agent system we will be building here, but I found it quite important to just give an overview how this works, because the vector store is not as easy as it sounds at the first glance, because you have to put some thought into it, how to structure your data, how to chunk your data, and so on and so forth. The vector store is very strong with the similarity search, but as you could see in this video, there are some points you really need to think about when it comes to chunking and how to represent your data in the vector store. And there are also more advanced techniques you can use. We will do that in a later video, how you can prepare the data for your vector store. So that's it from me today. Have a nice weekend. Bye bye.